Welcome to After Hours Engineering. In this episode, we build and review a very basic monitor program, similar to Dave Ho's style. And we introduce IRQs via CSRs, which we've covered in one of my previous episodes for Range of RISC. This episode would be way too long if I was to cover every detail of the monitor. So we're just going to cover the highlights, which includes trap vectors. In addition, we will again make a modification to the Femto processor to change and add support for trap vector interrupts. The intermissium doesn't come with the ability to write to the MEPC register. This is one of the CSRs that captures the return address for the trap vector when an interrupt occurs. So we're going to make an addition to writing to that, which means I need to move code around inside the Femto to handle that. So let's begin. Let's start with the monitor first and assume that the Femto is capable of doing everything that we'd like it to do. I'm not going to cover everything, of course. This is 2,000 lines of code, so it's not worth it to spend that much time. Up at the top, I've added an option in here for including or telling the assembler that we're going to use CSR instructions. Without it, we would get the unrecognized opcodes for CSR. So you'll need this line if you're going to use interrupts or in general just CSR registers. We have our usual defines up top here that we've seen before. I've added a couple of macros because I got tired of putting in a prologue and an epilogue type of stack manipulation, so I set those up. The program has its entry point here. As usual, we do some printing and configuring. We turn on the traps up here. Well, actually, we configure the traps. What this is loading is the MTVEC register that, if you'll remember from one of the Ranger series, we talked about CSRs. The trap vector is stored in the MTVEC register, CSR register. And then we go into our usual scanning for characters, checking for stuff. We've seen this before, and go around looping. Then we have another function here that isn't hit until a trap vector goes off, until an interrupt triggers. And when it does, we want to jump to the trap vector, run the code that's in the trap vector, and then come somewhere else to re-enter into the monitor. And that's what this does. It prints carriage returns, prints a message where they interrupted in the program. We'll see that in a minute. We also go ahead and grab the return address that was backed up from the trap vector itself. We'll talk about that down below, but we're going to now print it out, what the original interrupt was, the address where the interrupt actually occurred. And we're going to print that out on the command line in this format right here. And then we'll resume scanning, which is going to come back up here and start the whole thing over. We'll see all that. And then the rest of this is just standard sifting through every command to see what they typed and then processing it. And from here on down, there's a lot of code. We're only going to look at just the U and the X. Those are the most abundant ones that we'll use the most. The U is for uploading code, and we'll also talk about the upload side as well. But what this command does is it just comes down and waits for, puts out a wait message and begins polling for certain bytes to come in. And the first one that it's going to look for is start of transmission, or SOT. When it gets it, it'll fall down here, show us that it's getting ready to load. And then it falls into this large loop that's going to go around in circles looking for one of three signals. Now this is a half software-defined protocol. So the client is going to send data will need to have a delay between each byte. Otherwise, you'll upload junk and garbage half the time. And I'll show that again in the uploader. Basically, it's going to take the incoming stream and look for either signals that are coming in or data that's coming in. And it'll take that data and pile it into words. This is uploading code. It just doesn't upload random things. It'll upload code. Then we come down and look at the X command. And this is going to execute that code that we loaded in. And I'm going to show you a memory map in a moment that shows you where all of this is going and how it works. The execute command will show a running message, and then it backs up the monitor's stack pointer because the microprogram will probably have and will have its own stack pointer, and I'll show that on the memory map. We then enable the interrupts so that we can use the Control-C keyboard command to interrupt the microprogrammer running. And then finally we actually launch into the microcode itself, which is at a fixed location. We'll see that on the map. And then if the code isn't interrupted and it has some point where it exits, it'll actually come down to this code. We'll restore the monitor stack, disable the interrupts, and then print out a return message. The A0 register will have a return code, much like in a C language program where the main routine will return an integer of some number. That's exactly what this is. The A0 register will have a number returned from the microprogram. And that's it. Then after that is a ton of methods to sift them. We have our UART commands here. Here's the UART, 2 new UART methods for enabling and disabling the interrupt bit inside the control register. And then we come further down here, we'll see 4 new methods for dealing with the ISR instructions or configurations. Here we're setting the trap vector. This is where the processor jumps to when it detects an interrupt signal, whether we're enabling it in the M status register. The Femto only has machine mode. It doesn't have any other mode, so it's effectively only enabling and disabling machine mode. And here's the disable version of it right here. And here is the trap vector. This is the other end of the spectrum. When we hit Control C, the UART will generate an interrupt signal. It's sent to the Femto. The Femto will recognize it and send an acknowledge back, and we'll get into this routine right here. And of course we're going to back up the stack pointer because we're going to start manipulating different types of stuff in here. We don't want to mess with the monitor stack pointer. We're going to also disable interrupts. We don't want to have reentry in our interrupts, so we disable those. And here is where we go and store the address of where the interrupt occurred in the microprogram itself. We store that in memory, and we grab it out of the MEPC and we store it in this location defined by T01. Then we go ahead and find the re-entry code of the monitor and stuff that into the MEPC. So we're basically intercepting or hijacking the MEPC, and this is where I had to make an additional change to the Femto to support writing to the MEPC. The MEPC is a read and write, but not all architectures may actually support that. And in this case, the intermissium variant of Femto did not support it, so I had to add it in. And that's it. That's what happens. We'll see this all in play when we take a look at it. Over here to the right, we have the linker that's been slightly modified to support this new functionality. We had to bump up the monitor code segment to 5K as this code, 2,000 lines of code, was really starting to eat through the RAM. So we needed to bump all the other sections out and away from each other as well. And then finally we added this brand new code section down here that starts at 1F00. I put a gap of 256 bytes between them. And then I added a new section to support that memory definition right here. So now let's take a look at the memory map that supports both of these two files. Here's the memory map that supports that piece of code. Over here to the left we have the usual workflow or tool chains for generating the code that will go into the monitor section. Everything in purple here is the monitor. We have 5K for just the code, the ROM, the key buffer, and the stack. And then over here farther up we have the microprogram. And I've allocated 2K of bytes here, which, subtracting out the ROM and the stack, gives us 1280 bytes for a microprogram. It's not much, but it's enough to have a little bit of fun. We have a separate workflow for that, a makefile that will take the microprogram itself, output it a Verilog, and then we have a Go program here that will send it over to our monitor, and the monitor will load it right in here. And then up here we've seen where our port A and our UARTs are that we're defining. And then in the future, we're looking at the SD-RAM and potentially placing it at this address right here. So this is the memory map of everything that we're going to be covering. Now let's switch over to the HDL side and look at the kind of modifications we made to the code in order to support interrupts completely and fully. So we'll start with the UART component, which generates the interrupt. And here it is. That's the flag going out of the UART. And then we added this new one called the interrupt acknowledge. So some device out there is going to detect this interrupt and respond with an acknowledge to us. That device, by the way, is the Femto, but in general it could be any device. So if we scroll down here, we'll see where we made the detection. We needed to add a new variable that checks to see is the control flag enable bit set, and did the byte that come in happen to be the end of transmission, or control C. That's the value for a control C right here. Now this state and this state have always been there, but they've been a little bit different. We've added a check in here to see if the control C is detected, meaning the byte came in and the bit was set. If it was, then we set our interrupt flag to a 1. So some device out there, aka the Femto, will see this. And then we will transition into another state that simply spins around and waits for the acknowledge to come back. Now the reason why we did this is because the Femto looks at that interrupt on the rising edge of the clock. So if we look over here to the right, we can see that here's the rising edge, and the interrupt is sensing on the rising edge of the clock. Now the problem is that the UART, which is probably, and is in this case, operating a much higher clock, meaning in a different domain, could have raised and lowered its pin before the rising edge, or even during a falling edge of this clock right here, and we would never see the interrupt. And that's exactly what happened. I would hit the control C character and it wouldn't interrupt, but if I kept hitting it enough, eventually one would catch and I would get an interrupt. That's when I knew I needed to do some modification. And in this case, I added an interrupt acknowledge. That binds the two of them together. This is a relatively tight binding. You know, it's a small project, so it's worth it. So let's take a look at the Femto and see what kind of modifications we did to that. Of course, we added the acknowledge that is coming out of the Femto. The Femto is going to see the interrupt request and then acknowledge it. So if I highlight that and go down to our first occurrence, it turns out that the Femto is internally tracking it as a thing called interrupt accepted. And we just echo that right back out. Now if we look at interrupt accepted, it only happens when the interrupt has occurred, which is the sticky bit and all these CSR registers here, status and MCAUS, and we're in the execute state. In other words, just as they say in here, it says that it only recognizes interrupts during the execute bit. And that was the original problem I was having. I might have generated an interrupt, but it wasn't at the right time or at the right rising edge. So that is what corrected that. So now if we come down to line 491 here, we'll see that this is the MEPC. Remember, in our trap vector down here below, we were grabbing that value and storing it and then overriding it with our reentry vector. Well, originally the only place that the write was happening was during this clock domain right here, this positive edge. And I wanted to change it up above in another domain. So I basically replicated this code and moved it up top. So if we come over here and search for the MEPC, we'll see that right here up in this domain, which now is where all the CSRs are, is again, I'm checking for the state execute bit, the same interrupt as we did below, and there's that same code where it was moving the PC and put it in the MEPC. The addition that I made is if it's a CSR, these two were here before. The one I added was this one right here. And this one allows me to write into the MEPC. I need this so that this line of code right here works. Otherwise, without this line of code, we would have written into deep space and nothing would have happened. It wouldn't have worked. And that's it. That's the changes that I made between the UART, which is sending out the request, and the Femto, which is receiving the request, the interrupt, and then acknowledging it back to our UART. So with those additions in there, let's take a look at the uploader. And over here to the right, I have the very simple Go program that I wrote. Now remember, back here in our monitor, we had the detection of EOT and data and ADR. Well, the Go program is going to do just that. It's going to, whenever it detects an address in our hex file, it sends the ADR signal. That's what we're waiting for over here in the monitor. And when we detect it, we go into this loop, which grabs all 4 of these bytes that'll come in. And again, I had to put a delay in here because it's a one-way software protocol. And we store it all in. When we get all 4 bytes in, we then write it to the working address in our memory down below. Then it hits all the data bytes or the instructions base, and we start splitting those out across the wire in our send data. So if we look at send data, here's that DAT signal. And when that comes in, we skip down here. The ADR and the DAT look pretty much identical, except that one of them is going to simply update the working directory, and the other one is going to store it in memory based on what the working directory is. And that's what these two we're either going to go this path for an ADR or go this path for a data instruction. And that's all it does. It just spins around, and every time it finds an address, because different sections of code are at different addresses, skip around, that we send this. And that's all the uploader does. It's a pretty simple uploader. And once it's done, we print out a complete message down here below, and we exit out of the upload command. And that's it. Okay, so that's the uploader. The question is what does it actually upload? Well, it uploads micro programs. And over here on the left, we have one of them. We have the counter. And if you'll notice, it looks almost identical to the monitor. It's just simply assembly code using the gas assembler structure. And it also has a start, and it has a stack. It has its own stack, which is down here at the bottom, right here. So this has a tiny little stack. We saw that in the memory map. I'll show it again. And then we have all of our support routines. We have writing to port A, that's for counting, and then we created a simple delay method so it counts slow enough that we can see it counting, and that's it. It just comes in, saves any of its own local registers that it's going to play around with, then it resets the counter, and then it goes into a loop just sitting here writing and counting and writing and counting. Port A is the hello world for LEDs. It comes in, writes out the byte 42, and then exits. And hello world does the same thing, but instead it's going to write a string out, which is down here at the bottom, right here, string hello. We come up top here, we'll see that this is the same as all the other programs. They all have the same structure. They save their little stacks and they do their storing and restoring of the program counter. In this case, we need the UART offset. We're going to write the string hello just like we did in the monitor, and then exit. So what do those hex files look like when you compile them? They look like this. This is using the object copy GNU tool. Remember, we have the AS tool for gas, we have the linker LD, and now we're using the object copy to generate this code that can be loaded straight into it. Now you'll notice that this is in Word format, but we need this in byte format. So the uploader will automatically convert these addresses into byte format and store them in the correct location. And this 7C is exactly equal to 1F00, which is where we saw that this program will get loaded into and what we saw on the memory map. So now we're ready to jump right into the console and test all of this out and take a look at what happens. Over here to the lower left, we have the section where I upload the bitstream onto the FPGA, and I've already synthesized it, so all I have to do is upload it via the Tiger. On the upper left, we have the monitor itself, which I've already uploaded, and it's running here. So if I come over here to the Tiger, I can re-upload it, and you'll see that it reboots like that. Now we have a running monitor, and I call it a Ranger Retro. So we can examine memory. So we read word 5, it'll read 5 words, and now the monitor is inspecting itself because these are the actual instructions at the top of the monitor. We can also read it in byte format like this, and this is big endian order, but we can also now write to the port any values we want. We just need to set the working address, and Dave Ho's style was to actually set the working address. Over to the left of the cursor is the address. So if we go AW, we put in the address of the 2345 here. That's the address of port 5, and now we can write any kind of byte we want to it. So I'll write a 5. There's the 5. Excellent. So we should see the 5. And now I can write any other value like 42. And there's 42. I can write 55. There we go. Excellent. So let's go ahead and inspect, say, the key buffer. We know that the program, the key buffer the monitor has assigned it to 1A00, so we'll set the working address to 1A00. There it is. And now we'll read bytes 5 out of it, and there is what I typed in at the keyboard. So there's our read buffer right there. So if I type in read buffer 6 or 6 like that, now it says read 6. Oh, excellent. We can inspect memory right to the port. So let's run one of the bunch of the programs. So we'll upload the port A, We'll type the U command to start the upload sequence. Then we'll upload port A over here in the right terminal. There it's uploaded. And we can execute it. We should see that the LEDs turn to the number 42, and they did. Excellent. So now we can upload the hello program. So we'll upload that. We'll come over here to the right, type in hello, and it's uploading that program. And we can then execute it. We should see the word hello. Excellent. So it's uploading code and running them. So let's upload a program that doesn't exit when it's finished. And this is what it all comes down to, is using that Control C. So I'll hit the U command and I'll update the counter. And now I'll hit the execute to run the program. And you'll notice that the LEDs down below are now counting up to the FFF, or just F. And then they'll recycle around. So in this point, we're now stuck. We would have to reset our monitor, but because we went through the effort of adding the interrupt and detecting it in the UART, the Control C, we can now interrupt the program. And I'll hit the Control C, and there it is. It interrupted our program. The address that we see here is what the instruction was executing in our microprogram. So if I run the program again, you can see it's starting to count. I'll hit Control C, and we get a different address. So it just depends. Most of the time you'll get 1F6C because that's the tight loop that it's sitting there reading the control register for keyboard inputs and stuff like that. But there you go. We now have a monitor that we can move forward with and start doing some other things. Excellent. We now have a decent monitor for Ranger Retro and the ability to load in programs. However, microprograms are a little bit too small. We need something much larger to load programs into. And for that, we're going to need the Schoko's 32 megabytes of SD RAM. Now, this is not a static RAM. It is a dynamic RAM that looks like static RAM, which means it's certainly more complicated to use, including the refresh mechanisms and the wait states on it. At the moment, Schoko's bit streams were generated using LightX, and so it's kind of like a black box. So I either will have to take the time to isolate what LightX produced or look at the chip specs and try to figure it out from there. So I have no idea how long that's going to last or take. So until next time, peace.